So this is the total time derivative ddt of partial derivative of Laplace of Lagrangian function with respect to the generalized velocity. That means ddt of del L del Q j dot minus del T del L del Q j. That means the partial derivative of Lagrangian with respect to generalized coordinate. And that is equal to Qj. Qj is, I have defined this as generalized force, which is nothing but summation of Fi dot product Fi del Ri del Qj. So this is the definition of Qj, capital Qj, that is the generalized force. So with this in mind, we derived the equation of a motion of few systems. Today we will continue with that, but now instead of generally taking systems any arbitrary manner, I will consider systems just to show how many types of vibration problems can arise. Okay, or so to say, how the vibrating system can be classified. So I will take a first example, which is the simple example, maybe the simplest of all. This is this one is a linear spring connected to a mass, the simplest prototype of a vibrating body. So I want to derive the equation of motion. You can take the generalized coordinate from any point. You may take the distance from this, let us say, zeta as the generalized coordinate, zeta, which is a function of time. Okay, so if I write down the Lagrangian of this, so it is the kinetic energy minus potential energy. Kinetic energy, this will be equal to half m zeta dot square. Okay, zeta dot square. And what will be the potential energy? What is the potential energy?
Half k zeta square.
Minus half k. Yes?
Zeta square.
Are you sure? Zeta square?
No, sir, it's
Yes?
it will be displacement.
So like that will be the initial length, like zeta minus initial length.
Zeta minus zeta of t equal to.
So this may be, if I write down free length as, let us say L naught, free length, or LF. So you have to be very careful in writing down the expressions. Okay, you should not, if the spring is there, don't say that half k x square all the time. You understand what does this x mean? Otherwise it will be wrong. Now what will happen? Now del L, I need del L del zeta dot, which is equal to m zeta dot. Okay, del L del zeta, which is equal to minus k zeta minus LF. Okay. Lagrange equation will be ddt of m zeta dot minus of minus k zeta minus LF. Okay, and that is equal to 0 because there is no external force. Assuming that this is frictionless. Okay. This is frictionless. Okay. Now, so this will be the equation of motion. And if you write down the equation of motion neatly, then it becomes half. So this is m zeta double dot plus k zeta minus LF. This is equal to 0. Okay. So is this the equation of motion? Correct? I have this system, and this is the equation of motion. Is this correct?
Yes, sir.
Yes, sir.
But here, in usual case, you will have mx double dot plus kx equal to 0. Here, LF is appearing. That is not a very serious objection, because what we know, we can define x as z minus LF, and this is nothing but the displacement of the mass from the equilibrium position. This is how x is defined, displacement of the mass from the equilibrium position. And then if you substitute that, then x double dot will be equal to zeta double dot. LF is a constant quantity, so then you get mx double dot plus kx equal to 0. So this is our equation written in terms of x. X is now our generalized coordinate. Okay. Zeta is the generalized coordinate, but it is also the true coordinate of the mass if you consider this as the origin. So this is nothing but the coordinate of the mass. But z is nothing but the displacement from the equilibrium position, which is not definitely not a coordinate, but this can be considered to be a generalized coordinate. Okay. With x, if you know LF, you can find out the configuration of the system, that is the position of the mass with respect to time at any instant. Okay, so this is the equation of motion. I'll tell you, is this clear? I mean, this is a very simple system. I'm not going to spend much time on this one, but let me go to another example. Now, this one is K, this is M. I want to write down this equilibrium equation. Now, what will be our, what generalized coordinates should we take? What generalized coordinates should we take now? If you take this, the position, let us say y, as the coordinate, the y component, or if I, okay, fine. So this is what we have. Then I first write down the Lagrangian. This is the kinetic energy minus potential energy. What will be kinetic energy? Half m y dot square. And what will be the potential energy? What is potential energy?
Sir, half k y minus the
Half
initial
k
length.
y
Sir, y
minus
minus y
mg
dot.
y minus LF, that is the free length of the spring, and
mgh plus mgh.
and plus
minus mgh.
grab mg or into y minus lf.
why y minus LF? If I assume this as the y minus LF, you can take, it doesn't matter. But why y minus LF came into your mind? This is the spring stretch, so that's why half x square. But this is the change in the position. Change in the position means that if I take, that depends on the reference point. That is, if you take the LF length as your reference point, then y minus LF. Otherwise, I can take any reference point. This I take the zero reference plane for potential energy, this mgy, and I can take minus mgy. This is clear. So you may add anything y minus LF or any arbitrary thing, because what you are doing, you are changing the reference level only, nothing else. So if this is so, then del L del y dot, this will require, this becomes my dot, and del L del y, this will be equal to k, this is minus k, y minus LF, and plus mg. Okay. So the equation of motion ddt of del L del y dot, this will be my double dot plus k y minus LF minus mg, this is equal to 0. Yes? Okay. Now this is the equation we have, my double dot plus ky equal to k LF plus mg. So this is the equation. It has a forcing. Okay, there's a forcing term there present. right hand side. So it is not my double dot plus ky equal to that, this quantity. So what it means that, so even if y double dot equal to 0, there is no acceleration, y dot equal to 0. So there is a fixed point, that means there is an equilibrium position will be there, and this equilibrium position is not y equal to 0. So it has certain equilibrium configuration, so equilibrium position will be at a point where the force is balanced. You know that the equilibrium position, if you find out equilibrium position, then this will be k, let us say at equilibrium point, this y minus Lf, and this will be equal to mg. So ky minus Lf will be equal to mg. This will give you the equilibrium position. Okay, well, let us say y naught, so equilibrium displacement. So if you have here, you'll see that y naught is equal to k Lf plus mg divided by k. That means Lf plus mg divided by k. So this y naught, this part will be because of the free length of the spring. That would have been also the same thing had this been oriented in a horizontal direction. But because there is a constant force acting, so there will be another component in the stretch. So the spring will be stretched a little bit more. Okay, mg by k amount, just to take care of the gravitational force. Okay, so this is the equilibrium value of y naught. Now what we can do, we can define another, this is, let us say, this one, which is equal to y minus y naught. So this means that this is the displacement from the equilibrium position. Theta is equal to displacement from the equilibrium position. So if you define y by minus y naught as this one, that means y equal to eta plus y naught, then you can get from this equation m double dot plus k eta plus y naught equal to KLF plus mg. And because of this fact, that is y naught equal to Lf plus mg by k, you will see that these terms will cancel out, and you will get the equation of motion in y double dot plus k eta. This is equal to 0. So horizontal and vertical system consisting of a small spring and a mass will have the same equation of motion, but provided the coordinate you consider, that is the generalized coordinate, the variable you consider, this implies the displacement of the spring, that is the stretch of the spring from the equilibrium position. Okay, so this is the because there was one component in the vertical direction, so equilibrium was not at y naught equal to Lf but somewhere else, and if you consider that equilibrium configuration, then this becomes the equation of motion. Is this clear? Is this clear to you?
Yes, sir.
Okay.
Yes.
Now this is actually linear equation in single degree of freedom. So single degree of freedom, linear system I considered so far. Okay. You can consider similarly a spring but this one I consider as a non-linear spring. Non-linear spring, it means what? If you consider the spring, then delta versus spring force for the spring, suppose the spring actually is stressed by amount delta. This was the original length Lf. Now this has stressed by amount Lf plus delta. So if the spring is stressed by amount Lf, which requires a force F, then this is not for linear, it's just like this, F equal to K delta, but now either this may be like that or this may be like this. So F is a nonlinear function, let us say K times delta plus maybe K3 times delta Q. Let us say this is the form. Okay, so this is the nonlinear spring we have. Then how to get this is the spring force. Okay, so for that, if you want to find out the equation of motion, then first of all you have to write down the Lagrangian. So again, let us consider zeta as our coordinate. Okay. Although it is better to, it would have been more realistic had I put x, because x is actually the real coordinate. Zeta maybe could have been considered the displacement, but here I consider zeta as the real coordinate. So the zeta dot, and what will be the potential energy? Kinetic energy minus potential energy. What will be potential energy now? What is potential energy?
Integral of
If not del F.
What is that? And remember,
If,
delta is nothing but our y minus LF. Okay, delta is the, sorry, not y, zeta. Sorry. So this is the stretch, zeta minus LF. Okay, so this will be equal to half K1, maybe it is K1, I write down, K1 zeta minus LF square plus 1/4 K3 zeta minus LF to the power 4. This is clear why I have written this expression, all of you? Is this clear to you? Why this is so? Because the potential energy is nothing but minus F d zeta. Okay, so this is the potential energy, and if you just integrate, then this becomes the result. Okay, U equal to minus F d zeta. So that is the potential. The spring, the force is like that. So F equal to minus del U del zeta. So therefore, U equal to minus integral F d zeta, and therefore I get that. Alright. So here, if I take this expression, then I can get the del L del zeta dot. So this becomes equal to d dt of m dot minus of minus, so therefore this will be K1 zeta minus LF, okay, plus K3 zeta minus LF cube. This is equal to 0. Right. Now I'll substitute x equal to zeta minus LF as usual. Then I'll get this equation here, mx double dot plus k1x plus k3 x cubed. So this is actually a nonlinear system. Okay. And what kind of nonlinearity is this? Okay, so this is a nonlinear system. You understand that this equation is not a linear ordinary differential equation. This is a nonlinear equation of degree 3. So third degree nonlinear equation. Okay, so ordinary differential equation of order 2 and degree 3. Is this clear? So this is a nonlinear system. I will consider another nonlinear system. Is this clear to you? I mean, I am not getting any response.
Yes, sir.
Yes, sir, it is clear.
Here, degree will be 1 only, right? Like degree is defined as the order, power of the highest order differential.
This is a cubic differential equation.
Okay.
Okay. Cubic differential equation of second order.
Yes, sir.
Okay. Now let me consider another system where there is a guide and this mass can freely move along this guide, and I have here two springs. So this spring is connected. Okay. and it has length, let us say LF and LF. So when you displace the spring from this position, equilibrium position, then the spring gets stretched out. Right? So these are linear spring. Let me consider the linear spring for any displacement. This is linear. So I want to write down now what will happen. This mass will be displaced here, and if you leave it, then it will move back and forth. So there will be a vibration ensued on this. I want to find out this the equation of motion of this part. Now I can get any generalized coordinate, but maybe what will be easiest will be this one xt as the generalized coordinate. That means measure of its center, the distance of its center of mass from the origin point here, from the midpoint, from this point O. Okay, so this is the generalized coordinate. Now, if I write down the Lagrangian, so this will be the kinetic energy half m x dot square, and what will be the potential energy? What will be the potential energy? Can you please tell what is the potential energy?
Sir,
Yeah. 2 because there are 2 springs, so I write down 2.
Sir, half K.
Half A.
Where it is?
L final by initial square.
LF square plus x
We
square.
need to calculate final
So
length.
the final length. Okay, let me put here. So this is minus 2 into half K. Final length, what will be that? Final length will be,
LF square plus x square.
right, so this will be
Root LF square
LF square plus
x square
X square, right? And
minus
this minus LF.
whole
Yes, so this is so, isn't it?
into 2.
Half K times the change in the length of the spring.
Sir,
Yeah.
sir, isn't it like we subtract the final and initial potential energy of the
So
spring?
it will not, potential energy is like this. It's not final and initial potential energy. It's not final and initial potential energy. Potential energy is the half K delta square, that is delta is from the initial configuration.
No, sir, like if we integrate it between integral FTS, then it will be half k x square from initial to final. So that will be half k initial square minus final square.
Okay, so let me check. So this is LF minus this part. So this is our stretch. You mean to say this is half K LF square? Another term. That may happen. This is an additional term which may come. It doesn't matter. So this is the current kinetic energy, the current potential energy. And this was, actually this is, the delta was 0. So see, what is happening is that from K delta equal to 0 to delta equal to this value, this will be K delta D delta. So this will be equal to half K delta square because delta was 0. So initial potential energy is 0.
Yeah, yes, sir.
Okay, initial potential energy is 0. There was no deformation. So initial potential energy is 0. Otherwise, we would have taken the initial potential energy, but here initial potential energy is 0. Okay. Now, if you think about it, I think if you think a little bit, then you'll get this doubt clear. So if your equation, if your Lagrangian is like this, then the equation of motion will be mx double dot plus this will be d dt or del x of del x of this quantity which will be equal to 2 times this will be what will be that? This is 2 times k whatever is this. Okay, so we'll get that value. So this becomes equal to 0. So mx double dot plus 2k, and this will be 2k, and this is x divided by under root 11 square plus x square times I believe I have done it correctly. I will see, but this is what you will get. This is also derivative of this quantity. Okay. So you see, this is actually a nonlinear equation. You please carry out this differentiation. It's not difficult. So I think I have done it correctly, but you will check. But what I want to say is that this becomes a nonlinear equation. Okay, nonlinear equation, and this is the nonlinear equation. Now, earlier we had one kind of nonlinear equation. Now we are having another equation. Here we have a spring, which is a linear spring. Okay, so what is the difference between these two kinds of nonlinearity? Both of them are giving nonlinear equation. So what is the difference? What is this difference? Now, in one case, the nonlinearity was in the spring, and if you take the spring to be kind of modeling the elasticity of the body on to which the mass is connected, so this is actually this appears nonlinearity in the earlier case can be thought of appearing because of the material property nonlinearity. So, not the stress-strain relationship is not nonlinear, not linear in that case, but here stress-strain relation is linear definitely, but now because of the geometry, the arrangement is such that the nonlinear terms are coming. So there are two kinds of nonlinearity which you come across in your later courses if you take nonlinear vibration also. So there is one kind of nonlinearity which is known as the material nonlinearity. And another type of nonlinearity is geometric nonlinearity. I hope the difference is clear to you. For example, if you take a vibration of a continuous body which is made of nonlinear material, that is where the Hooke's law is not valid. Okay, the stress is not proportional to strain. Which is a stress may be a nonlinear function of strain. You can get the equation of motion. So this is a material nonlinearity because the nonlinear equation will be because of the material property, nonlinearity in the material property. Other type of nonlinearity is because of the deformation. Okay, that is the geometry is such that the nonlinear terms are coming, isn't it? So this is very basic difference between these two kinds of nonlinearity, and I hope with these simple examples you have got the essence of it. So very basic idea about what is the difference between material and the geometric nonlinearity. Okay, so we had, so one can classify a vibrating system as a linear system, and nonlinear system. Okay, then in this particular situation, we had no forcing. Okay. Let us have now a force present on it. So let me name this force as Ft, which is a function of time. So a time varying force is actually acting on that. Now with this, actually the equation of motion, we have to consider the very general equation del L del Q I dot minus del L del Q I equal to capital Q I, where I equal to 1 to n, the number of degrees of freedom of the system. Okay. Now here in this case, I have written earlier, this is equal to half k. If I consider this as zeta, then sorry, this will be L will be equal to half m zeta dot square minus half k zeta minus LF square. And what is Q? The generalized force. Generalized force, you see, this is by definition, this was for all particle I equal to 1 to n, Fi dot del Ri del Q J. So this is the definition of Qj. Now in this case, actually there is a single particle, so this is not needed, summation is not needed. So we have a single one, so this will be F dot del R del here zeta.
Sir, one
So
question.
what is F? Yes.
Sir, the Q, sir, the QJ which are sir, that is the non-conservative force.
This is a non-conservative force.
Okay, sir.
Okay, because I have already taken the conservative part inside this L. Otherwise, you could have taken conservative force. Does not, I mean, it does not do any harm. Maybe you could not detect that there is some force which is conservative. Maybe you did not know that. Okay, just you took the force and you did not notice that this can be taken inside L. Does not matter. You take whatever you can inside the L, the Lagrangian equation. Rest of this part you leave within the generalized force. It will do the same thing. I mean, there is no hard and fast rule that all the conservative force you have to consider in L.
Okay, sir.
Right? Whatever you
Okay.
can, you make.
Okay,
Okay.
sir.
So Q in the F is equal to Ft in the I direction, and R is nothing but Zi, zeta I. So in this case, del R del zeta is nothing but I, and Ft. So F dot. So Q here is Ft I dot I, which is equal to Ft. Okay, so this is the generalized force. Now I can write down the equation of motion of this very simply as m zeta double dot plus k zeta minus Lf equal to Ft. Okay, it's equal to Ft. Fine. Or if you define x as zeta minus Lf, then the equation of motion will be mx dot plus kx equal to. Okay, fine. Now this kind of excitation, so this is the equation of motion of the forced system. Mx double dot plus kx equal to Ft, which is the forcing. Now here this kind of, well, the forcing, so the forcing can be of many types. Any function can be actually taken as a forcing function. There is no restriction. But this can be classified into two things. One is the deterministic. That means you can determine the function if you know what is the function. So one case it will be the deterministic. And in the other case, this is actually a random. That means probabilistic. That means you do not know exactly, but you have certain measure which is known to you. Certain statistics of the function is known, but the exact nature of the function, exact value of the function you do not know, but you can have some idea about the function. Okay. So here this function can be either random function or a deterministic function. So accordingly, the equation of motion will lead to the study will be the deterministic system or in the random system. So there may be a random vibration where the force is not known. Only the statistics of the some some statistical measure of the function is known, but the function itself is not precisely known. So this will be random vibration, and otherwise the vibration which we will study in our course, this will be deterministic system. Okay, so everything is determinate. The random vibration, of course, well, I'll come to that later on. So this is the broad definition of system, maybe linear, non-linear, both. So either deterministic system or the random system. Now here, with this response, you will study in a subject known as a random vibration. So this is the course in which this kind of situation will be dealt when the force is random in nature. We are not going to learn much about the random excitation. What will be the nature of response if the excitation is random? That we will not study. We will study only for the deterministic system. That is, this function can be actually written in a very nice way, and that is determined. Okay. So there is no probability involved in this particular system, so it is deterministic system. For random vibration, we are not going to study here. So random vibration you may learn later on. So here one kind of forcing was there, but now let me consider another system. So what it is shown here, the mass is connected to a spring and the other end of the spring is connected to a movable rigid body, which is a massless or having mass, does not matter. But these bodies actually moved with a pre-specified displacement function. So it is given a velocity. Now this velocity is controlled this is at our disposal. We can control this velocity. Whatever we want. There is a controller. I did not show the controller, but there is a controller which gives a measured displacement to this body, to this body connected to the roller. So this can move back and forth. So you understand that when this moves, the spring will be stretched because it will, if it remains stationary, then it moves. Then the spring will compress, and then it will transmit the force to the mass, and the mass, as a result, will start moving. So this is another way of giving excitation to the mass. Earlier we just give the force to the mass directly, but now I am exciting the base of the system, but this is actually excited indirectly by giving a displacement excitation. So I am exciting the mass indirectly in this manner. Now if you consider the Lagrangian of this, so this becomes equal to L half m zeta dot square, and what will be the kinetic energy, the potential energy? What is the potential energy? What will be the potential energy of this? Half k. What is the potential energy?
Zeta minus LF square.
Zeta minus LF. Anything else?
Square.
Minus x naught.
Minus x naught. This is a function of time. Okay. That is square. Okay. So this comes because the spring stress, the spring length at any time will be equal to x minus zeta naught, and the initial spring length was LF. So therefore, x minus zeta naught minus LF. This was the spring stretch. Okay, this is the spring stretch. Okay, so here we have then del L del T, so del L del zeta dot equal to m zeta dot, and del L del zeta equal to minus a zeta minus LF minus x naught. Okay, so equation of motion will be m ddt of this quantity, that is m zeta double dot plus k zeta minus LF minus x naught. This is equal to z, which is a function of time. Remember, this function of time is appearing, but this quantity, this expression does not involve zeta dot, so therefore we do not have any time derivative of zeta dot. So this equation, again, if you define zeta minus LF, then this becomes equal to mx double dot plus kx equal to kx naught. So this is another excitation, but this excitation is given to the base. So this is actually displacement excitation. The earlier excitation we considered force excitation. Now this excitation is displacement excitation. The excitation is in the displacement. Okay. So this is displacement excitation. So earlier we had force excitation. Now we have displacement excitation. So if you have understood this part, then if I can go forward, then definitely I can say that the excitation can be
Sir,
force or in the displacement. And also it can be also deterministic. Just a second, I'll come. And random. So these are two ways of classifying the excitation, either force.
Sir, please do not immediately.
Yeah. No.
Sir, please
Yes.
do not erase immediately. I cannot write anything. Sir, please do not write erase immediately. It's difficult to write down.
I suggest you do not, I mean, you pay attention to what I am saying. You will write definitely, but if you understand, then you can write on your own. You need not copy blindly and then this thing. There you will face difficulty because you may not understand what you have written later on. So first I said that you first understand, then you write. If you ask me to repeat, I am here, but please understand it before writing. Yeah.
So, like in the previous example, we did not consider the motion of the initial, like, exciting mass, right? Like, how is it different?
No. Okay. Okay, let me. This actually I wanted to avoid, but since you have raised this question, I should explain. Suppose it has a mass A and this has a mass maybe m naught, which is a very small mass. Or maybe write down here big mass. And this is a small mass. Or that could be also big. And this is given a displacement. Okay. Zeta naught t. Fine. Okay. Then suppose this is what we have and this is our origin. This point is our origin. Okay. Now this is actually a 2-degree of freedom system. Isn't so? Where you have two masses, right?
Yes. Yes.
Okay. So if I write down this as zeta 1, which is nothing but x naught, let us say. Okay, zeta 1, and let me say that this is zeta 2, second mass. Okay, zeta 2 and zeta 1. So we have our this Lagrangian. This will be half m zeta 1 dot square, half m zeta 2 dot square. Sorry. Zeta 2 and this is zeta 1 square. Fine. And the kinetic energy and the potential energy, this will be half k zeta 2 minus zeta 1 minus LF square. Correct? Is it correct?
Yes, sir.
Okay, good. Then I have to have this zeta 1 dot. This is equal to m zeta 1 dot del L del zeta 2 dot equal to m zeta 2 dot. Okay, del L del zeta 1. this is equal to minus, this is minus del L, so minus, this is plus K zeta 2 minus zeta 1 minus LF, and del L, this you please write down, del L2 equal to minus K zeta 2 minus zeta 1 minus L. Okay. This is clear? Correct?
Yes, sir.
Right? What I have not considered in this particular situation, there is something wrong in this particular situation, in the Lagrangian, or in the in this particular system. Can you say what is the wrong? This is very important to see. I say that this is moving with particular x naught t. Okay. So if I control this motion, if I can control this motion, so how this control is possible?
By
How
some external force.
by giving a
External
force.
force.
Right? This force is required, isn't it? Without force, I cannot control it. Otherwise, it will be its own motion, so I cannot have any control. I want a controlled motion to this base, isn't it?
Yes.
Okay, so I have to apply a force here in this particular system. Otherwise, we cannot control. There is a control force required just to maintain the motion. Okay. Otherwise, this will move like a free body, free motion, which will have its own dynamics. I cannot have any control over it. If I am to have a control, then I'll have to apply a force. With the force, I adjust the force such a way that the motion is adjusted. This motion can be controlled. So this is the minimum requirement. I need a force here, F1t. So Q1, you can say that Q1, if you just do the same thing, this one will be equal to F1t. And Q2 will be 0 because there is no, Q2 will be equal to 0. There is no force acting on this mass. Or this mass, you check that this Q2 will be equal to 0 and Q1 will be equal to Ft. Because Q2 will be equal to, you see the force on this will be F1 dot del R1 del Q2 plus F2 dot del R2 del Q2, and Q2 means that this is zeta 2, this is zeta 2. F2 equal to 0, there is no force acting on it, and R1 is zeta 1i, so therefore this partial derivative, this is equal to 0, so therefore Q2 will be equal to 0. So I have Q1 equal to Ft, Q2 equal to 0. Now if you write down the equation of motion, so please take this. So if you write down the equation of motion, this will be ddt. The first equation will be ddt of del L zeta 1, so therefore m zeta 1 dot, and this minus k zeta 2 minus zeta 1 minus Lf, this is equal to F1. This is the first equation. And the second equation, this will be equal to ddt of m zeta 2 dot, this plus k zeta 2 minus zeta 1 minus Lf, this is equal to 0. Okay, now what I am saying is this one, that is zeta 1 is a displacement, and this displacement I am by force saying that this zeta 1 is equal to x naught t. Zeta 1 equal to x naught t. That is what I am saying, and this actually gives us the same equation as we have earlier got. But what is this other equation giving? If you put, you can calculate zeta 2 from this equation, if you know zeta 1 x naught t. From this other equation, you will get F1, because if you solve this equation, zeta 1, this is x naught t, so therefore in that case this will be equal to x naught dot t. This will be equal to zeta 1 I said x naught is a function of time. So this equation will give you the force which is required to maintain this motion. And since I did not bother at the first instance what is the force required, so I did not consider this term. So, and that means that I consider only, it did not matter whether I consider the mass of the base or not. Okay, so because this did not appear here. But truly speaking, this is the way one should approach to the problem. Okay, because if you otherwise, I remove the dynamics of one system altogether from the very beginning. This did not affect it. But if you want to take this into account, then you'll have to include it in a proper manner. I hope you understood.
Yes, sir. Understood.
Right? So, is this clear? Why I did not consider the other? You should, and I think you could, and you should have considered it. But then you would have got the force which is required to maintain the motion. Fine.
Okay, sir. Fine.
Oh, good. So here this was one case. Well, let me take, this was the base motion. Let me now take another motion. Let us say a pendulum. Again, a pendulum, which then L and this one. And this time, the mass is moving with, let us say, this is the x naught t. So its mass is moving with displacement. This is actually base is displaced with given a displacement x naught t. So this is actually control function. Well, again, like the previous problem, I am not considering the dynamics of the base. Otherwise, if you want, you can do that. I am not doing this because of the obvious reason which I explained earlier. Okay, now this is the equation, this is the system. And now if you consider the, let us say this is the reference point where x equal to 0. And this position is, let us say I am measuring this as the, okay. So this is our position and the base is moving. The base is moving, so but this is a fixed reference point. Reference frame. I need inertial coordinate frame. So x naught is fixed, x equal to 0 is fixed line, and the base is moving with respect to that line. Fine. I need to know the Lagrangian function, so therefore the kinetic energy. What will be the kinetic energy? What will be the kinetic energy? Half m velocity square, right? Right? And what is the potential energy? What is potential energy of this?
minus mgx.
Right, minus mg x. Fine. So now let us calculate the v.
Sir, there is no rotating part in theta.
I will come because I expressed this one, and I know x is equal to, from this I use the geometry and I get x equal to x minus x naught. Fine, x equal to x naught plus L cosine theta. Right? And what is the velocity v? If I take this as I and j x coordinates, so therefore this will be equal to x naught I, which is a function of time, plus the relative velocity, right? And the relative velocity in that case will be equal to what? This will be, what is the relative velocity? It will be L theta dot E theta in this direction, right? E theta and E r in this direction, so this is equal to E theta. Okay, I know, of course, E theta is equal to, this angle is nothing but theta, So therefore, E theta will be equal to minus sine theta I plus cosine theta j. Okay, E are equal to cosine theta I plus sine theta j, and E theta will be equal to minus sine theta I and cosine theta j, because this angle is nothing but theta. Clear? It is a little bit of vector manipulation. You should be able to do this at this stage. E theta is like that. So this becomes equal to Lx. This is x naught minus L theta dot, then sine theta I plus L theta dot cosine theta j.
That x naught is the velocity excitation.
No, it is x naught is the displacement. X naught dot. Oh, okay.
Oh.
You are right. You're right. Thank you. X naught is the displacement, so x naught dot I should have written. Yes, please correct it. X naught dot, not x naught. Okay. So v dot v, here it will be equal to x naught dot minus L theta dot sine theta square plus L theta dot cosine theta square. If you take that, okay, then this will be x naught dot square minus 2 x naught L theta dot sine theta plus L square theta dot square. Right? Okay? Fine. Then I need to know the del L del theta dot, which will come from the mass term. So therefore, this will be L theta dot. So this will be ML theta dot, ML square theta dot. From here, there will be 2, and then this will cancel with half m. So this half. Theta dot will come from here also. So therefore, this is equal to minus this 2 will cancel with half. So therefore, x naught L sine theta, right? Please tell me if you have any doubt. I take the derivative with respect to theta dot, so this term will contribute also.
Sir, mass will also come in the second term.
Yes. Mass.
So x naught dot will be there, right?
Okay, so I'm missing something, so you need to be careful. Sometimes I'm leaving the next thought. Thank you. I hope this is correct. Okay, del L del theta, del L del theta. This will one will contribute from here. This is half m, so this theta will appear. So this will be equal to minus m x naught dot L theta dot cosine theta and mgx. So this is nothing but x equal to, let us say, x naught plus L cosine theta. So this will be equal to plus mg this will be plus mg sine theta, right? Plus mg sine theta. Fine. So this part is clear. Is okay? Okay. So now the equation of motion will be now d dt of this quantity, that is ml square theta dot minus mx naught dot L sine theta plus del L del theta, so mx naught dot L theta dot cosine theta minus mg. I believe this was as minus mg x sine theta. Negative term. So let us check the sign of this one. When you check, this was minus mg x naught plus L cosine theta. So del L del theta was plus term, but L. So this was the negative u, but u had L minus t minus u. So therefore L is equal to t plus this term. So therefore this will be equal to this will be plus, as I said, mg sine theta, because here we have t plus mg x naught plus this one. So del L del theta will be equal to del L del theta will be equal to minus of this part. Okay, minus, and when you write down the equation, that is minus del L del theta, then this becomes again plus, and that must be equal to 0. So please check this part. So whatever I am
Sir,
doing, yeah.
Sir, that should be mgl sine theta.
X plus L sine theta. Yeah. So mg L sine theta. Please check this. I mean, please correct this term. I made the mistake several times. So minus mg L sine theta will be there in del L del theta, and when it comes to the equation of motion, it will be plus mg L sine theta. You are very correct. So what I have here is that ml square theta double dot. I'll take just one more minute and then I'll let you go. So this will be equal to minus mx dot double dot L sine theta. This will be minus mx naught dot then L sine theta times theta dot. I have to take the derivative with respect to time. So derivative sine theta, cosine theta, and times theta dot. Chain rule is applied in this particular situation, plus mg x naught dot L theta dot cosine theta, and this plus mg L sine theta. This is equal to 0. It gets cancelled out, and you'll get ml. So ml square theta double dot plus m L. So it will be g sine theta minus x naught double dot I believe I have done it correctly. So there will be this g minus x naught fine. So this is the equation of motion you get. Now here this equation is different from either other type of excitation which I get. So this is like either without this x naught dot, it was mg L sine theta, but now this term is appearing. This term is appearing as a coefficient of the sine theta term. Earlier case, the equation, the excitation term appeared as inhomogeneous term in the equation of motion, but now it is actually appearing ml square theta double dot plus ml times g minus x naught double dot. So this is a kind of different type of excitation which is appearing as a parameter of the system. So otherwise it was mg, but now it is g minus x naught, and this is time value. So this kind of excitation, which is actually changing the parameter of the system, is known as a parametric excitation. There are many systems where the excitation is parametric, and these dynamics, the dynamics of the system may be little complicated. We are not going to study it, but just you remember that there is a thing called the parametric excitation, which actually changes the parameter of the system. Excitations are two kinds, as I said, that direct force excitation, direct displacement excitation. Another kind we have studied, this is the parametric excitation, where the excitation is done given to the parameter of the system. So eventually, although we are exciting the changing the display position of the base, but the equation of motion becomes such that the parameter of the system, so the coefficient of sin theta term, which was earlier constant mgl, now it has becomes time dependent. So this is known as a parametric excitation, and this is known as a parametric excitation or parametrically excited system. I hope this is clear to you that how this equation is different from the other type of excitation which we have studied. That is the force excitation and the displacement excitation. It is a new kind of excitation which I call parametric excitation. Okay, so next class I will study some other form of system with the help of the same Lagrange equation. So I am doing it intentionally for two purposes. One is to give you an idea about the different types of vibrating system which we normally have, which we study in the vibration engineering, and how to use the Lagrange equation, deriving the equation by Lagrange technique. So that is the dual intention I have for this kind of lecture. Okay. Okay. So tomorrow I'll consider the same thing. I'll go ahead with that, and then we'll have a small tutorial where I'll ask you to derive the equations using Lagrange technique. Okay. So this will be there will be some 3-4 tutorials problem which you have to solve here and submit. Okay.
Sir.
Yeah.
Okay.
Sir, like, in this course, like, do we know methods how to solve those equations, or only we need to derive the equations? Like,
no. Because derive the equation is the first step. Unless you know how to derive equation, you cannot actually go ahead. This is the first step in any system engineering. You'll have to first derive the system of the equation, the governing equation, which you have to solve later on. So this is the first step in this particular analysis, that is how to get the equation of motion. Once you get the equation of motion, you can use any mathematical technique or any maybe sometimes these days numerical softwares. So these are useful, but you have to derive the equation, and there nobody can help you. Okay, you'll have to derive on your own. Okay, equation derivation is not possible by computer. Oh, maybe sometimes these days the symbolic operations are possible, but normally we do not rely on this computer for deriving equation. We have to do on our own. At least you know how to do that, so that you can instruct computer to do on your behalf. Okay, so this is the intention. We have to know how to derive the equation of motion. Things come, other things, analysis, the solution, etc. will come later on. But first of all, first thing you must know is how to derive the equation of motion. If you do not know that, then there is no point in learning the techniques of solving. Okay, then you can become at most a subordinate to your engineer. That is, you have to solve, but you never can be a leader in that field. Okay, so this is the objective. Definitely, will from the next from Friday onwards, we'll go towards solving this equation. Okay? And the equations will be sometimes very, very difficult to solve, but we'll try to do that. And I suggest that we use the technique of transform calculus. You should read, if you want, I mean, if in advance you may read Laplace transform technique and Fourier transform. These we will use very frequently in the coming classes. Okay?
Yes,
Okay, na?
Yes, sir.
Okay, good. So I think I have exceeded time by 10 minutes, so please forgive me for that. If you have any doubt, you may